relax, and fall into Event Horizon with John Michael Godier. In today's episode, John is joined by Dr. Seth Shostak. Since the age of 10, Seth developed an interest in extraterrestrial life when he first picked up a book about the solar system. He has a degree in radio astronomy and is a senior astronomer at the SETI Institute. Dr. Shostak is also keen on outreach activities, interesting the public in science and astrobiology. He's co-authored a college textbook on astrobiology and has written 3 trade books on SETI. In addition, he's published more than 400 popular articles on science, including regular contributions to NBC News MAC. He gives dozens of talks annually and is the host of the SETI Institute's weekly science radio show, Big Picture Science.
Seth Shostak, welcome back to the program.
Thanks so much.
Seth, now, there are many interviews of you out there regarding SETI and radio astronomy in general. And as we were talking off air, hydrogen clouds. But also, you made a weird discovery in the 1960s, I assume very, very early on in your career, regarding dark matter and something misbehaving, a discrepancy with, as we recall, galaxies, motion. Tell us about that.
Yeah, well, for my thesis work, and this was back in the 1970s, early 1970s, and late 1960s, I guess we began then, was to study galaxies using radio telescopes and to measure the hydrogen emission from the gas in those galaxies. Now, a galaxy's got plenty of stars in it, typically a couple of 100 billion stars, but floating between the stars in any galaxy is all this neutral hydrogen gas. It's just hydrogen gas. It's very, very thin. I mean, the density is very low. It might be 1 atom per cubic centimeter, which is better than any vacuum you can make here on Earth. But space is big, and as a consequence, you get a signal from that neutral hydrogen gas. And this was figured out by the 1950s. People had measured it. And I was using it to just study the galaxies. I was studying the hydrogen emission from nearby galaxies, which told you one very important thing, namely, how quickly are they spinning? And what I found was, to my consternation, was that they all seemed to be spinning much faster than was expected. And for a long time, I figured I'd made a mistake somewhere in the software I was using for my thesis. But eventually, I just published the result that they were spinning too quickly. And that was one of the earliest and maybe the most significant indications that the universe is filled with something called dark matter. That's what was producing these galaxies that were spinning too quickly.
Serendipity, you just happen to notice it while looking for something else?
Yeah, well, but that's a very common story in science, in research, and in astronomy in particular. You know, you're studying one thing and you find something else, and that's what was going on here. As I say, that's not so unusual. It took a long time for me to really realize how significant it was, to be honest. But anyhow, we just published the result that the galaxies were spinning too quickly, and that was, as I say, one of the earliest indications of dark matter in the universe. And of course, we still don't know what the dark matter is, but we know it's there.
So I assume when you're looking at the spin of a galaxy, looking at the hydrogen, when you're looking at the spin of the galaxy in radio, you see a blue shift and a red shift profile, right? Is that how that's done?
Well, it's true. That's correct. That if you had a hydrogen cloud that wasn't moving either toward you or away from you, then the frequency would be exactly 1420.405, whatever, megahertz. Right, that's just a lab measurement, and it's based on some very fairly simple physics, actually. But because a galaxy is rotating, all galaxies are rotating. I mean, some rotate more than others, but because they're rotating, it's like looking at a phonograph record, if you will. If you look at a spinning phonograph record, one side of the record's coming toward you, the other side of the record's moving away from you. And, that's exactly the same thing that would happen with these galaxies, that one side's coming toward you, the other side's moving away from you. And that shifts the frequency of this hydrogen emission that you're measuring. So what you can do is by noticing this frequency shift, you can determine how quickly the galaxy is spinning, depending on where in the galaxy you're talking about. And that all sounds kind of boring, but it's not at all boring because it tells you how much mass is in that galaxy. That's just Newtonian physics, goes back hundreds of years.
Yes, and it's delightfully a discrepancy because now we talk about dark matter all the time. We still haven't found out what it is, but there are a lot of people that have interesting ideas, WIMPs and things like that, new particles that are non-interactive, sort of like maybe some type of cousin of the neutrino, something like that. And it just sort of sparked all that off, that discrepancy among the galaxies. And more importantly, why aren't they flying apart? And there must be gravity. It's that simple.
Yeah. Well, they wouldn't fly apart because the spinning's not fast enough to cause that. But it is, as you say, it was extremely puzzling, and it still is in the sense that, well, we know the dark matter's there, but what is dark matter? I mean, that's just a euphemism. It's just two words that we can use to kind of cover up our ignorance. There's something there, but we can't see it, and that's why you call it dark matter, because it doesn't emit any light and it doesn't seem to emit any other kind of radiation. So we don't know what it is. Galaxies could be filled with footballs, for example. That might be a lot of matter if you had a lot of footballs, and you wouldn't be able to see them because they're not very bright. And I doubt that it's footballs, but it could be something that's maybe fairly prosaic, but we just don't know that it's there.
And it's pretty amazing because it shows, which obviously that's not a very good terminology, but we'll use it. It chose the weakest force to interact. And I always found that weird. So it doesn't do electromagnetism, doesn't do any of the others that we know of, but it does do gravity.
I mean, it is gravity. That much we do know. I mean, it's just acting, gravitationally. But in order for you to have a gravitational force, which, as you say, is a very, very weak force, I mean, you need some matter. You need some stuff there, right? And we don't know what this stuff is.
Now, what can radio astronomy do to further dark matter research? I mean, is there areas that you could go into beyond just gravity, or is that just something for the particle accelerators and other means?
Well, I mean, I think that the general assumption by physicists, and they probably know more than anybody else when it comes to this question, is that dark matter consists of, some sort of exotic particle. You named a couple at the top of the show here, very tiny particles that may exist in these galaxies, that may exist everywhere, and that there's enough of them to account for this behavior that the dark matter, I mean, it has to be a lot of stuff. In fact, the dark matter is maybe 5 or 10% of the total mass of a galaxy. A galaxy is a pretty heavy thing. There no bigger things in the cosmos other than galaxies, no individual things. And so it could be that there are just a lot of sort of very tiny particles that permeate these galaxies, and that's what it is, axions or whatever. But we don't have any proof of that. I mean, we still don't know. Dark matter has been a mystery now for decades, and we still don't know what it is. And by the way, in the meanwhile, we've also found that the universe is also permeated with dark energy, and we don't know what that is either. So in some sense, this is kind of it's a damning discovery that 95% of the mass of the universe is in dark matter or dark energy, and we don't know what either one of them is.
Yeah, but it keeps things interesting. The universe never gets boring. Now, when looking at the hydrogen clouds in your early research, that frequency, and you mentioned it, 1420, is also where SETI looks. It's in the watering hole, that range of hydrogen emissions from radio emissions from hydrogen. How does hydrogen do that? So how does neutral hydrogen produce a radio signal?
Yeah, well, it has to do with the behavior of a hydrogen atom. If you remember back to high school physics, a hydrogen atom, which is the simplest kind of atom, it consists of a nucleus, which is just a proton, right, surrounded by one electron. That's the simplest atom there is. Neutral hydrogen, a proton and an electron spinning around. But it turns out that there is that both the proton and the electron have spins. They spin. I mean, you tend to think of this in terms of something spinning that you know about, something macroscopic. Of course, at the atomic level, spin has a slightly different meaning, but never mind all that. That's freshman physics. But because of the spin can be in one direction or the other direction, and every now and again, a hydrogen atom will collide with another hydrogen atom, and that'll flip the spin, right? And when you flip the spin, you produce a photon of energy, a little bit of radio energy, and that's what causes the 1420 megahertz hydrogen emission from galaxies. It's these spin flips. And the chances that if you took a single hydrogen atom and you put it in your spare bedroom and you sat there and watched it, waiting for it to flip, for the spin to change, you would wait a long time. Right? The sun would probably be gone by the time it happened. But if you have lots and lots of these hydrogen atoms, as of course you will have in a galaxy, the fact that any given one doesn't flip very often, you've got so many of them that the spin flipping is happening all the time. So you see this emission of radio. It produces a little bit of radio emission, and that's easy to measure.
And of course, any scientist in the universe is going to know this, which is why it might be a good place to look for alien signals. What led you to start pursuing SETI from studying hydrogen?
Yeah, well, you're right. I mean, people who are doing SETI, they're trying to prove that there are aliens out there by eavesdropping on signals, and in particular radio signals has traditionally been one of the ways to do that. It was the first SETI experiments were always in the radio. But the question is, okay, you're going to look for ET's radio transmissions, but unfortunately, ET never sent you an email telling you that this is where you ought to be looking on your radio dial to find these transmissions. However, as you point out, everybody will have this 1420 megahertz frequency marked on their radio dials, because this whole business with the hydrogen emission, I mean, that's something that any advanced society in the cosmos is going to know about. So they will all know that frequency. So it was suggested very early on that if you want to find ET signal, well, look somewhere near this natural emission by hydrogen, because everybody in the universe who is technically competent will know that frequency. And if they're deliberately trying to get in touch, they'll put a signal near there because they know you will know that frequency too. That's all it is.
Are there other signposts, chemical signposts, evident in radio like the hydrogen line?
Yes, there are. For example, there's also an emission line produced by what's called the hydroxyl radical. And all this is a hydrogen and an oxygen atom that get together to produce something called OH, obviously OH. And that also produces radio emission. In fact, lots and lots of things produce radio emission. But the OH produces radio emission. That was worked out rather early. And the frequency at which it does that, I think it's around, I don't know, it's a little higher frequency than the hydrogen emission. And consequently, people said, well, look, if ET's really trying to get in touch with us or anybody else, they're going to broadcast at a frequency that we're already going to know, because obviously they can't send us an email or a radio transmission saying this is where I'm going to be transmitting, because if you knew that, you wouldn't need that email, right? So they figured, all right, everybody will know about the hydrogen line, and they'll also know about this hydroxyl line, this OH line. And H and OH make H2O, that's water, and this region of the radio dial is called the water hole, because H2O is water. And it just happens to be a range of radio frequencies that everybody in the cosmos who's technically competent will know about. And consequently, if you're looking for a hailing frequency, if you're looking for a deliberate transmission by sophisticated aliens, then that's a reasonable place to look. That's a reasonable part of the radio dial to explore.
And it also happens to be water, the universal solvent that life's chemistry occurs in, and it's the best one. I mean, there are a few alternatives, ammonia and things like that, but water's a good one, and that too might play into their decision to send a signal at that frequency, just because it's a commonality.
Well, yeah, water's all over the place. I mean, the universe is filled with water. There's water everywhere, and we believe that water is useful for fomenting life. Without water, we wouldn't have life here on Earth. Water is, yeah, as you say, a universal solvent, but more than that, I mean, water seems to be an essential component of the chemistry of life, at least here on Earth, and presumably elsewhere as well. So, yeah, looking where this, in this so-called water hole, that range of frequencies makes sense, because that refers to a compound that is probably essential to life, and we know that, and the aliens will know it too. I mean, it's what you're trying to do is guess where they might transmit a signal, where on the dial they might transmit a signal, and all these arguments point to this particular range of frequencies.
Now, the other way you can do it is try to monitor as big of a swath of the radio spectrum you can, with, presumably splitting it into channels. So how wide of a range can you search around the hydrogen line these days? I know that very early in the 70s, it wasn't very far, 50 channels, something like that. How many do you deal with now?
Yeah, well, our experiment deals typically with a few billion, with a B, channels. And that's a lot. I mean, as you point out, the electronics of the 1970s would allow you to monitor, you say 50 channels. That's not terribly far wrong. So, that was a lot. We thought that was a lot. But, of course, the number of possible channels on the radio dial is huge. I mean, so the more that you can monitor, the greater the chance, presumably, that you will pick a winner, that you will have tuned into the right frequency, the right channel, to actually hear ET. So the ability today to build receivers that can monitor billions, with a B, billions of channels, obviously seems to increase the chances that you're going to pick up a signal.
Now, before we move on, I have an odd question that occurred to me. So you're looking at the hydrogen of distant galaxies and watching them spin. Can you do that with the Milky Way? Does the Milky Way give you a red and blue shift signature from a different perspective that shows you its rate of spin?
Yes, of course you can. And in fact, the early hydrogen measurements by radio astronomers were of the hydrogen in our own galaxy. I mean, you can just, we're in our galaxy. That's part of the problem. So that makes it a little bit more complicated because you're in the rotating record as opposed to looking down on it from a couple of feet away. And that complicates things because the plastic used to make the record is transparent, if you will. And so you're seeing deep into the galaxy when you look in almost any direction. And consequently, there are going to be clouds of hydrogen that are coming toward you, and there are going to be clouds of hydrogen that are moving away from you, and so forth and so on. But again, this was all worked out very early, when I say early, by the 1970s, and people were using this technique, this ability to observe this moving hydrogen, to map out a picture of what our galaxy looks like, at least in terms of the gas in it. And again, it's high school geometry, really, but, it's a little more complicated than looking at an external galaxy.
So when you get a star-forming region where you have a lot of hydrogen, what's that look like? Is it just hopelessly broadband because everything's just smearing around? Or can you get a meaningful profile of the formation of a star from a radio measurement?
Well, not from the stars. The stars don't produce any hydrogen emission. In fact, stars don't produce very much radio emission at all. Most of their emission is in, light, visible light, or infrared, or ultraviolet, or whatever. But you can, in fact, as I say, measure the hydrogen in your neighborhood, and of course it's moving in all sorts of different directions. But overall, you can determine the motion of the hydrogen nearby, and even the motion of hydrogen that isn't very nearby, because radio telescopes look right through the gas and dust between the stars, so you can see hydrogen clouds that are very far away on the other side of the galaxy. This is a great tool for mapping out the galaxy. I mean, this is a question that anybody would have had 30, 40 years ago. What does our galaxy look like if we could somehow get in a rocket and zoom away a few thousand light years, or a few hundred light years, whatever, and look back at our own Milky Way galaxy? What would it look like? I mean, it's just an interesting idea. And by measuring all the motions of this hydrogen gas, we can figure that out. And you can just go online or anywhere else, and you'll find pictures, maps, if you will, of what our galaxy looks like. It has spiral arms and so forth and so on. And all that was due to mostly measuring the hydrogen gas using radio telescopes.
Now, stars being weak emitters of radio seems to me to be helpful for SETI searches, so you don't get that much interference from stars, right?
Well, you don't. No, you don't. But you're looking for a transmitter, right? And everything produces a little bit of radiation. I mean, even your kid brother produces some radio radiation because he's warm, and anything that's warm is producing light, mostly things like infrared, because otherwise your brother would be easy to find in the dark. But it also produces radio radiation. So, yeah, I mean, it's a very useful technique. I think that more than anything else, mapping the hydrogen of the universe has told us more about the universe than almost any other technique that we use.
Yeah, I remember I was an amateur astronomer, still am, for 40 years now. And I remember trying to build a radio telescope to try to pick up Jupiter with a shortwave radio. Did you ever do anything like that?
No, I didn't, but there was, I had access to, if you will, very large radio telescopes at national facilities. And it turns out that if you have a big telescope, you can do a lot more than you can with a small one. Radio astronomy is not a discipline that really offers amateur astronomers very much that's terribly interesting. If you're an amateur astronomer, better to have a telescope that works at visible wavelengths, at light wavelengths, at something that you look through or put a camera on, that kind of thing. And there are amateurs who build radio telescopes, but they can't build anything very large. They can't build an antenna that's 100 feet across, for example. They just don't have the resources to do that. Consequently, amateur radio astronomy has never become a big thing.
No, looking for Jupiter is about all I ever could try to do. Now, radio telescopes. We lost Arecibo, obviously, structural failure, which is a big hit. And of course, there's FAST in China, which is comparable. But do you think we need to rebuild Arecibo? Or do we need to go with a completely different design?
Yeah, well, that's a really good question for which I don't have a particularly good answer. The estimates for rebuilding the Arecibo radio telescope, which was, 1,000 feet across, right? 305 meters or something like that. It was a big antenna. It was, put in a big natural bowl down in the karst landscape of Puerto Rico. You could rebuild it. People have considered what it would cost to rebuild it, and the estimates are roughly $100 million. Well, that's not nothing. That $100 million is real money, and if you have $100 million to spend on a telescope, are you getting the most bang for your buck by building a duplicate of Arecibo, which in some sense, as you just pointed out, is hardly necessary because others have built telescopes that are that big, and you might as well use theirs. So I think that if that kind of money is available for a new telescope, it probably isn't going to be rebuilding the Arecibo telescope, which is a shame. I really enjoyed using that telescope. It was always a great adventure to do that, but that's probably not where you'd spend the money these days.
Yeah, that area of Puerto Rico looked cool. Just the landscape, with the, like you said, the karst topography and all that. How remote was Arecibo? I mean, was it near town, or was there, what facilities and amenities as an astronomer did you have when you were down there?
Yeah, well, to say it's remote is a relative term. It wasn't terribly remote because it was about an hour's drive from the town of Arecibo in northern Puerto Rico. And Arecibo is maybe not the most interesting city in the world, but it's not in a jungle that's very remote from society. I mean, if you want to go out for an ice cream or a sandwich or have lunch in town, okay, maybe you'll spend an hour and a half or 2 hours on the road total, but you can do that. It's not that it takes days to get to this thing. So, yeah, it was in the karst region, the K-A-R-S-T, karst region of northern Puerto Rico, and there wasn't much else there, but you could always go to nearby towns. I mean, Puerto Rico is very densely populated. I think it's probably the most densely populated place around on Earth in some sense. So there are towns everywhere, but it's still, it's not that there were a whole bunch of people living where this observatory was built. The telescope was built in what was previously a tobacco farm, I believe.
It's not over yet. Join me as we continue to travel through the cosmos on a gentle wave into Event Horizon.
Now, interference is always going to be a problem because we're transmitting like crazy. Are there entire areas of the radio spectrum that are just simply too full of human interference to even search?
Well, there are plenty of them because obviously the radio spectrum is, if you will, a natural resource that many people have use for. And if you're competing against, the military that wants to set up some radars and so forth that are operating at the same frequencies that you want to use for radio astronomy, guess who's going to win that battle? They're going to win. But on the other hand, there are regions of the radio spectrum that have been set aside, if you will, sort of like, a national park is set aside. And there are parts of the spectrum that have been set aside for the use of astronomy. And they're not very much of the radio spectrum. They're fairly small sections of the dial, but those, people have recognized you got to try and preserve some of this free of terrestrial interference. The real solution to this problem is just to go to the backside of the moon, which obviously is too expensive for us to do right now, but eventually you'll be able to build radio telescopes on the far side of the moon, and there you're shielded from all this interference coming from the Earth all the time. And that would be a real boon because it would be relatively interference-free.
Now, interesting signals. Have you recently gotten any? Is there any anything stand out as of late?
Yeah, people do ask. They say, "Have you heard anything?" And then my answer to that is always pretty much the same. If we had heard something, you would know about that, because that would be a really big discovery. We're looking for signals all the time, but if we had found one, at first you probably wouldn't even believe that you'd found what you're looking for, that it was really ET. You would want to check that out, and it would take a couple of days for you to do some tests to make sure that you're not being fooled by radar down at a local airport or something like that. But we haven't found a signal of that. And if we had, it would be front page news. I mean, Americans love to believe in conspiracies, but there's no conspiracy in science research. I mean, if you were to find this signal, the first thing you'd do is write it up as quickly as you could, send it to a journal, and tell the world. I mean, it would be a big story. So if we had picked up a signal that really looked like it was ET, you would hear about it.
Well, there's also the tricky situation that SETI is global. So there are plenty of places on this earth, almost 200 of them, that the U.S. government wouldn't be able to keep hushed if an alien signal was found. But again, you're right, people do love conspiracy theories. Now, the Fermi Paradox...
I was going to say, the other thing that always puzzles me is, why do you think the government would want to keep it secret? I mean, even if the government could keep it secret, which, as you point out, it really couldn't, but even if they could, why? Why would they want to keep that secret?
I don't see why a distant radio signal halfway across the galaxy or, multiple light years away would change anything other than humans' viewpoints. We'd be like, oh, there they are, we are not alone. Profound question answered, but I don't think that everybody would go crazy over it. In fact, I think people at this point expect it, that eventually a signal will be found.
Yes, no, they do. Surveys have shown repeatedly for the past decades that most Americans, at least Americans, believe that the aliens are out there somewhere. A surprisingly large fraction of them think that the government knows this and is keeping it quiet. But as you just point out, the United States is not the only country in the world with big radio telescopes. I lived in Europe for a long time, and they have big I was using them. They have big radio telescopes there, too. And the idea that the Dutch government, because I was living in Holland, the idea that the Dutch government would somehow figure that the populace was going to go nuts if they heard that we picked up a signal from ET. I mean, that just didn't compute. It didn't make any sense.
Especially with the Dutch government, I don't think they would care. It would be good for the radio astronomers, though, because number one, you'd win a Nobel Prize, and number two, you'd get more radio telescopes to figure out more. And that's another thing, is that it seems to me, you find a good signal, that means funding, right? And find out everything you can about this apparent alien civilization. But you haven't seen it yet. And as you say, no good signals yet. Does that tell you anything about the Fermi Paradox? In other words, do you have a gut feeling of a solution to the Fermi Paradox based on radio astronomy?
Yeah, the Fermi Paradox, for listeners who might not know what that is, it was just an observation made over the course of a lunch by Enrico Fermi, the famous physicist, in 1950, as I recall. 1950, and he just said, between two bites of his sandwich, he said, so where is everybody? In other words, the universe has, obviously lots of stars and even a greater tally of planets. There are planets everywhere, and most of those planets are, if you will, like Jupiter or Saturn, not terribly interesting for life, but, some of them will be interesting for life, and the universe is so large that there must be, literally billions, hundreds of billions of societies out there of intelligent beings. So the question is, why is it that we don't know about a single one of them? We haven't found any intelligence elsewhere in the universe. In fact, we haven't found any life elsewhere in the universe, right? And so he was just, puzzled by this a little bit. He thought if the universe was really crowded with intelligent societies, we would have had some evidence of that by then. We haven't, and you ask, well, why is that? And of course, we don't know why that is. But I think that the straightforward answer to that question is simply that we haven't checked out enough of the cosmos. We haven't looked everywhere. I mean, it's like saying there's buried treasure out there in the Pacific. Why haven't you found it? Well, they haven't looked in the right place yet, whatever. So I think that that's the answer. I think it's just a matter of this whole idea of looking for ET. It's a fairly new idea. It goes back maybe to the Second World War or something like that. So say 70 years. And so we're just getting started, and the fact that we haven't found anything so far shouldn't be something that disappoints you.
Now, it's interesting to point out here that a lot of SETI experiments, most of them, right now are targeted, looking at individual stars and individual targets. But there's another possible approach, all-sky SETI. What are your thoughts on the idea of going more broadly with our radio telescopes?
Yeah, well, what you're talking about are the kind of SETI experiments where you do what's called if you will, an all-sky survey, where you kind of sweep the antenna around slowly, or just go from one spot on the sky to another spot on the sky, and you cover as much of the sky as you can looking for a signal. And on the one hand, you can say that's obviously the better strategy, because we don't know where ET might be. We don't know where the signal might be coming from, so let's just check out everything. But the price you pay for that sort of an approach is that you don't have very much sensitivity, because you're only spending a fairly short amount of time looking in any given direction. And it's better if you can zero in on parts of the sky where you think there's a better chance of finding ET, and those would be places like the directions of nearby stars, for example, because we know that maybe 70 or 80% of those stars have planets. And even if you don't know whether any of those planets are good planets, with oceans and atmosphere and all that sort of stuff, just looking in the direction of stars would be a better strategy. I mean, it's like saying you're on a South Sea island and you're looking for the buried treasure that was left there a couple of hundred years ago, and there's parts of that island that are better places to start digging than others. And that's sort of the approach that SETI takes. We try and second-guess the aliens.
Now, radio strikes me as being something like fire. I mean, we harnessed fire, actually, archaic humans. we actually, as Homo sapiens, inherited it. So we harnessed fire, but today, hundreds of thousands of years later, there are more fires going artificially on this planet than there ever has been. Radio seems to me, and a lot of people say, well, aliens don't use radio anymore, that's quaint. But it seems to me to be something like fire, a natural attribute of the universe that will never stop being useful. However, there is one area of SETI possibilities here that does seem to be very fruitful to look, because we can, and that is laser SETI. What's your view of searching for laser signals?
Yeah, well, you're quite right. I mean, my view coincides with yours. I believe that radio as a technology will never go away, because it's a great way of sending bits of information from one place to another. And I'm not talking about, whether top 40 stations will still be around 10,000 years from now. They may or may not be, but the use of radio as a technology will be, and consequently I think that radio SETI will always be a good thing to try. But there is this other approach, which is to look for flashing lights in the sky, maybe, lasers flashing at you. And it's called Optical SETI or Laser SETI or whatever. So instead of looking for radio signals, you're looking for flashing lasers. And that's being done as well as the radio approach, maybe a little bit less of it, but it is being done, and I think it's a great idea. I mean, you don't know what the answer is, so let's try various things.
Well, it's interesting because you're not going to mistake a laser. You're going to know that that's technological in the same way that, a narrow band transmission in radio would do it. It's like, not a lot of ways this can happen in nature. I mean, there are a few possibilities, but mostly it's just going to be technology if you see it.
That would be the first assumption. But it's true that there are things called masers, for example, which are natural lasers that exist in the cosmos, too. So you have to, you obviously have to check things out and make sure that you're not being fooled by a natural phenomenon. That happens a lot, particularly in astronomy. I mean, the pulsars for a long time were called little green men. Maybe not terribly seriously, but they were called that because there was these very regular radio transmissions, and people figure, well, the only way that could be happening is if there's some alien sending these signals. Turns out it was completely natural, but yeah, you've got to check that. You've got to be careful not to fool yourself.
Now, when you pick up a radio signal, say with the Allen telescope or array or whatever radio telescope, when you pick up a signal, you're going to naturally see the raw radio energy of it. But how do you tell if there's any kind of data in there? Can you tell that, or are you still just looking at raw emissions and bandwidth of it? Or can you see things like modulation?
Well, of course, you would tell that it's a deliberate signal if it changed. Modulation just means that the signal is changing. I mean, just think of, I have a ham set up upstairs in an upstairs bedroom, and it produces a signal if I'm using CW. In other words, I'm sending Morse code, which is basically just a continuous tone that you turn on and off, right? Following the Morse code alphabet, for example. And so you could say, well, how would you recognize that? Obviously, you don't know ET's Morse code, so how would you know? Well, you just look for a signal that is spread a little bit across the radio dial. That tells you right away that it's worth looking a little more carefully at that to see if it's changing, right? If it's changing rapidly, and instead of just being like noise, there's some changes in the signals. You have no difficulty recognizing music coming out of your radio as opposed to the static that you pick up between the stations, right? So it's something analogous to that. You would be, I think, fairly quickly able to tell whether a signal has any information on it or not. Now, having said that, that doesn't mean you'd be able to ever figure out what that information is. I mean, you know, it would be their Morse code in their alphabet and their language, and you might never figure it out. But at least you would know that this is not just an empty signal, that there's something in there, there's information in there, and I'm sure that a lot of time, energy, and money would be expended trying to figure out what they were saying.
Now, say you have a signal that by its nature doesn't really contain information, but I say this because one of the strongest radio signals we emit is radar. And that's the one thing that at a distance might be relatively easy to see from us. When Arecibo was radaring asteroids, of course, it didn't repeat, so the aliens would call it a wow signal. But still, if you saw that, how would you differentiate a radar from, I don't know, a radio station, an alien radio station?
Yeah, well, you might not be able to. I mean, radar, as you say, it kind of mimics an empty signal because it doesn't carry any information. You won't learn the nightly news by listening to radar signals. So it's possible that there could be that kind of a signal that you pick up and there's no information in it. Now, you know, this comes up occasionally at conferences with scientists sitting around, and they figure the aliens aren't going to spend a lot of money to send a signal into space, to build a big transmitter and beam a signal into space if it doesn't have any information on it. What's the point? It's like running telephone wires to all the houses, but never allowing people to get on the phone and talk to one another. So that's maybe too much sociology in a way, but I think that the idea that there could be a lot of empty signals out there doesn't make a whole lot of sense because it's expensive to produce a strong signal, and you're only going to do it if you get some benefit out of it.
And that brings us to my next question. So it has been pointed out in the SETI literature that maybe aliens are opportunistic and they don't make these big transmitters to just throw out radio energy on a lark. Rather, they would wait for another signpost, say a supernova. So when, say, a supernova were to cook off, it's been a while since we've seen one, but say one cooks off in the Milky Way, would you immediately turn your radio telescopes at it?
Well, I mean, that would be a decision that would be made by several people, I'm sure, but people have done that. People have said, look, if a supernova goes off in your neighborhood, say you're Joe Alien, and a supernova goes off, 10 light years away from you, actually, you'd want it a little farther away than even that, I suspect. Otherwise, it might wreak havoc on your atmosphere and stuff. But in any case, some supernova goes off in your neighborhood. You know that any other intelligent societies out there in the galaxy are going to be looking your way because they're all going to want to study that supernova. I mean, it's not a SETI experiment for them, but there's much to be learned of astronomical interest by studying supernovae. So they're all going to be looking in your direction. If they're all going to be looking in your direction, you might try turning a transmitter 180 degrees away from the supernova, if you will, in the opposite direction, where all these observers are, and just send them a transmission of some sort. Hi, we're the Earthlings, and we'd love to get in touch with you guys. Whatever. So people have suggested if you want to find ET, maybe the best thing to do is look in the directions of supernovae.
I believe there was also a paper that I read where they said, okay, look at propagation. So as the supernova explodes, when information of that supernova arrives at a promising star system, look at it. Because maybe they transmit only when there's some serendipitous occurrence in the galaxy, and that's when they do it. So you could do that approach too, right?
You could. But of course, it's not very specific, doesn't it? It might limit your search at least, so you don't have to look everywhere. I mean, it might limit it to, if it's a supernova that's gone off in the past 100 years or something like that, there might only be a couple of hundred, maybe a few thousand star systems that have seen that supernova, and you could look in their directions. You could do that, but if you're not in the direction of the supernova seen from their planet, they might not be broadcasting in your direction. They might just be broadcasting, if you will, 180 degrees away from the supernova as they see it. and consequently you might not be in the right part of the universe. So it's maybe of limited use, this idea, I think.
Now, in regards to where an alien would be located, what are your thoughts on looking at the center of the galaxy? Or is it just hopelessly radio confused to even look there, and maybe it's not likely that life could arise in that kind of a radiation environment? What do you think about looking at the center of the galaxy for SETI signals? Because you got a lot of stars packed in a very small area.
Yeah, I'm all for it. In fact, I think my first published paper that had anything to do with SETI was the result of a survey we did looking at the galactic center, saying that, look, if you're a really advanced society and you can actually build rockets that can travel between the stars, one place you might want to consider going, or at least sending some instruments, is the center of the galaxy. Because the center of the galaxy is where all the stuff is, right? There are a million times as much stuff per cubic inch, if you will, at the center of the galaxy as there is, in our neighborhood. And all the technologically sophisticated societies will know this. And consequently, if they want more energy, they want more stuff or whatever for their gusto-grabbing lifestyle, they may indeed move to the center of the galaxy or send their equipment to the center of the galaxy. So looking at the center of the galaxy, our galaxy, or even the centers of other galaxies, it makes sense from the standpoint of SETI, I think, because whatever else, the galaxy has many societies for sure, and some of them are going to be able to send stuff to the center of the galaxy, and maybe there's a big hub of whatever down there, and we should see if there's any signals coming from it. But people have looked, I've looked, haven't found anything special coming from the center of the galaxy yet, but there's always the question of whether you're looking in the wrong part of the radio dial or you just don't have enough sensitivity. But I think that the radio searches in the center of the galaxy have been done for a long time. It would only make sense to keep doing it.
Now, I guess the same would be true for globular clusters, right?
Well, globular clusters, again, for listeners who don't know what a globular cluster is, it's just a big ball of stars, maybe tens of thousands, hundreds of thousands of stars, and a big ball. You can see them with a small telescope because there are plenty of globular clusters, which just means ball-shaped clusters of stars. Really, that's what it is, in our own galaxy. But the thing is about globular clusters is that we know from astronomy those are very old stars. They've been around for a very long time, but they were also formed early enough in the universe that they're, some of the elements that we think are useful for life, like oxygen or whatever, carbon, they don't have too much of those so-called heavy elements in them. And consequently, the planets that might be in a globular cluster are also kind of devoid of these useful elements. And there may not be that much life in globular clusters. There are plenty of stars, but maybe that's not the best place to look for life.
Yeah, and that brings up the question of phosphorus, because the distribution of phosphorus in the galaxy seems to already be spotty, and it is absolutely crucial for our type of life. But I wouldn't imagine there'd be very much of it with very early stars and globular clusters, right? I mean, that would be a big showstopper, I think, no phosphorus.
Well, yeah, that may be. But you don't have to wait too long for stars to cook up some of these interesting elements. I mean, phosphorus, if you really want phosphorus, buy a bunch of matches, get a lot of phosphorus that way. Within a few billion years after the Big Bang, there were stars that around that were big enough to cook up some of these elements and then eventually sort of vomit them into space. And a few billion years, that'd be a long time to wait for a bus. But a few billion years is actually not all that long, given the fact that the universe is 13 billion years old. So I wouldn't be too swayed by the idea that we should look only where there is phosphorus. And there's enough phosphorus all over the place. And yes, it's essential to our biology and maybe to ET's biology too, but it isn't that there are places in the universe that are completely devoid of phosphorus. The universe is made of the same stuff everywhere. That may be the biggest discovery of science, of astronomy in any case, in the whole history of astronomy. The fact that we see that the universe is the same almost everywhere. It really doesn't matter where you live. The neighborhoods are all pretty much the same.
The Copernican principle. Now, galaxies. Extragalactic SETI, looking at other nearby galaxies. Is there a radius where you just say, look, we're looking at that galaxy so far back in time that it's elemental poor, just like the globular cluster, it's elemental poor. Is there a sort of radius where you just say, no, these galaxies are write-offs past a certain distance?
I don't think so. I mean, there's some kinds of galaxies that you might not look at for possibly other reasons. But look, because all the elements that we think are essential for life, at least life as we understand it here on Earth, they were all cooked up, within a couple of billion years of the Big Bang. The Big Bang goes off, and then maybe 3 billion, 5 billion, whatever, years later, there's enough of these heavy elements, as they're called, but particular carbon and silicon and all these things in the universe to support any sort of life, that it really, you can't look far enough back in time to get to an era when these elements didn't exist. Yes, in principle, if you look maybe 11 or 12 billion light years away, you could say, well, whatever I see at that distance, that's so far back in time that they don't have much in the way of these elements necessary for life. That could be. But if you're looking at anything that far away, don't expect to pick up any signals because they're going to be incredibly weak after traversing that kind of a distance. So I don't think that this really affects the search very much.
Yeah, but it does. It's very important for astronomy to look that far back with JWST, because that is one of the things, the grails that I want to see astronomy do over the next few years, is finally glimpse a population 3 star that's just unbelievably early and prove that those things exist. Now, my last question for you is a very extreme environment that perhaps highly advanced aliens might find it useful to go and set up shop around a black hole. Can a black hole be a SETI target to search, or are the emissions from that thing, from the accretion disk, just overwhelming and you're not going to see nothing?
Well, no, I think black holes are a good target. In fact, I also did an experiment. We looked at a couple of nearby black holes. Now, keep in mind, there are black holes everywhere. Big stars, when they die, they often form black holes. They collapse in on themselves. So there are black holes that aren't terribly far away. Within a couple of hundred, couple of thousand light years, there's some black holes, the grave sites of dead stars. And you might say, well, why would you look there? I mean, you don't expect many aliens to be keen on setting up shop near a black hole because it's a dangerous place in some sense. But on the other hand, you can get a lot of energy out of a black hole, actually, it turns out. So it may be that there are societies, really advanced societies, that do choose to live near black holes, and maybe it's worth looking in the direction of black holes. And yes, they can, in fact, be radio emitters. Black holes often are. But, these kinds of, if you will, everyday black holes, the kinds that are produced by the death of big stars, they're not such dangerous places. You could, if you were in orbit around one of these black holes at a distance that's comparable to our distance from the sun, for example, it wouldn't be dangerous in any sense. So it may be that that's another good place to look.
Yeah, just don't get too near it. And don't go inside. But if you've got that, you've got a lot of possibilities. And I remember one particular paper by David Kipping, the Halo Drive, about how to gain acceleration by using a black hole, and it just seemed like there is a lot of unique things there, and there's a lot of energy, especially with an accretion disk whirling around this thing, that just seems there for the taking. And a lot of people seem to take the black holes off of the possibility for aliens, but it seems to me that might be an ideal place for an advanced alien civilization to go in their old age.
Well, it could be. I don't know if it's the best possibility, but it's certainly a possibility, and you shouldn't rule it out just because a lot of people say, oh, black hole, that's dangerous. No alien will hang around there. As you point out, it might be a good place to go because you get a lot of, you can get a lot of energy, of course, by just throwing your trash into the black hole. But you can also, there's also a lot of radiation often associated with black holes, and maybe you could get some of that as well.
Yeah, and it has to be said that, nothing is going to live quite as long as a black hole. Just take an unbelievable amount of time for that thing to evaporate. So it seems that the end of the universe, at the very old age of the universe, that's where everyone will be.
Yeah, well, that's a long time from now. By then you have other problems. But the death of the universe, which we can actually say a lot about because it's, in the end, only physics and a little bit of astronomy, we know a fair amount about how the universe is likely to end. And, of course, it doesn't ever really end. It just keeps going on forever. But it gets very, if you will, very quiet, and it gets very dark. And eventually there's not enough energy in the entire cosmos to cook a marshmallow. That's a long time from now, of course, but that's inexorably what's going to happen. And again, we know that, the aliens know that, and that opens up a whole other line of discussion. Is there any escape from a dying universe? Can you somehow manipulate time and space to allow you to go to another universe, which might not be quite so old and things are still happening? Again, that's a physics question, and even if it's possible, it's not something we can do.
Yeah, well, maybe that's a solution to the Fermi Paradox, is that they all leave. There's a better universe that once they hit a certain technological level, they're like, we'd rather be there, and that's why we never see aliens.
That could be, but that would be like being a resident of Hawaii in the year 1000 A.D. and saying nobody's ever going to leave these islands because they're the best of all possible worlds. Maybe not true.
Indeed. Thanks for joining us today, Seth, and I look forward to another conversation in the future. And good luck with the SETI efforts. And I hope that that candidate signal finally comes soon.
Me too. I think that would be great, and it would also be job security. So I'm all in favor of it.
Absolutely. Absolutely.
Fall into another episode of Event Horizon and let us take you to the dream dimension.